Okay, hello everyone. I'll be talking about wastewater and stormwater infrastructures in context using systems-based approaches. I hope that at some point we can discuss how the main idea can be tailored for the state of Oklahoma. The first project dealt with two coastal communities that are vulnerable to the impact of climate change and extreme events. Adopting wastewater infrastructure or resource recovery systems and transitioning into an improved treatment portfolio require navigation of complex interaction between human, engineered, and environmental systems. So we looked into two case studies, one in Belize, Central America, where the decision-making process is consumer-driven and there is no specific regulation to comply with. This next one is Florida Keys in the U.S., where a policy-driven approach promotes the installation of centralized and community-based infrastructures. So for Belize, a group of environmental anthropologists, systems engineers, and environmental engineers work with the community at household level, and we identified the key variables influencing their decisions for adopting this wastewater resource recovery systems and how they maintain it. So we used some relevant social theories, interviews, and surveys, and combined it with the theory of mass conservation to build a system dynamics model and identify the socio-technical strategies improving the adoption of that new technology and sustaining it. By running that model, we were able to do sensitivity analysis, and eventually we ran the model over the course of 60 years, and we were able to recommend some courses of actions. The other case for the Florida, so we used a multi-level perspective on technology adoption. Because the system is policy-driven, so we look at the population growth. We also look at different extreme event frequency and duration, also some strategies for cost allocation at municipality level, and eventually some wastewater quality standards. By building this framework and systems dynamic, we were able to study lower key, middle key, and upper key in terms of two performance measure, nutrient loading and reliabilities. Eventually, we were able to identify three main socio-technical strategies and their trade-off for Florida case. So the next project is about integrated water and wastewater system. Here you can see the future of wastewater management, which is a hybrid form of centralized, decentralized, and on-site treatment system. So the challenging question is, how can we identify the configuration of the system across scale? So we suggested to look into this problem through the lens of reverse logistics, which has been used in manufacturing system for a long time. In reverse logistics, we look at both forward and backward flows in the network. So for water, we'll start with raw water and some treatment facilities for potable water, and then we collect the waste, and there are different scenarios for water reuse. So using this framework, we are able to do capacity analysis, considering different treatment technologies and water reuse scenarios, and minimize the cost, carbon footprint, and embodied energy. So we applied this integrated framework, the City of Lakeland water and wastewater systems. So we identified several water reuse scenarios, including indirect potable reuse, direct potable reuse, and agricultural reuse. And we were able to quantify each scenario based on economic, environmental, carbon footprint, and eutrophication, and some social indicator and identify the best scenario for them to move forward with. So in this project, we not only look at the water systems, but also look at the transportation system and their interdependency, as infrastructures are physically, virtually, and socially interdependent. And the last project is basically about the stormwater and some implementing green infrastructure and considering the organizational governance and private sectors and also a landowner. And here we are collaborating with some researchers from the UK as well. So, thank you.